Right. One with a bunch of quadratic equations to solve, and the other one with a bunch of quadratic inequalities to solve. Now, in these 3 questions, the instruction doesn't specify you to use a particular method. You have learned how to solve a quadratic equation using 3 different methods: by factorizing, by completing the square, and by using the formula. Now, all these equations given in these 3 questions can be factorized, but I don't know which method you used. You have the freedom to. You had the freedom to use any method you wanted. You could have just used the calculator to plug in ABC and use the formula. That is completely okay, right? Because using the formula is one way of doing it, and you are allowed to use the calculator. In advanced level, to solve a quadratic equation, you are allowed to use the calculator. So if you have done that, that is fine too. So let me quickly read the answers. If you don't need to look at the questions, I will just show you the answers. While reading them out, I will also show you. So this number 5 question, these were actually from the textbook. So the reason why I sent you a picture was because not everyone has the textbook. So the 5th question, it's actually in the exercise 2B. When you have your books, you will see. It is the 5th question in exercise 2B. So I will quickly read out the answers. If you want me to explain anything, please stop me and ask, okay? Number 5, part 1. Give me a moment. Yeah. Number 5, part 1. X is equal to 8 and X is equal to 3. Right? Part 2, X is equal to minus 8 and not and or X is equal to minus 3. X is equal to minus 8 or X is equal to minus 3. Part 3, X is equal to 2 or X is equal to 9. X is equal to 2 or X is equal to 9. I hope you are correcting your work yourselves. Please do that. Part 4, X is 3 or X is 3. It's a repeated root. So you do get two solutions, but they are not distinct. They are repeated, so they are the same. So it's just one solution. We talked about this last week. Why we say 2 distinct solutions or 1 solution? What does distinct mean? Here, you do get 2 solutions, but they are not distinct. They are not different. They are the same. So it's just 1. And the last one in that, 5th one, X equals minus 8 or X equals 8. Right? Hope everyone is okay with that. Then let's move on to the number 6. Number 6, part 1. Please stop me. Okay. Sorry. Please stop me if you have any doubts. I think I have a. Okay. It's fine, Lishan. Thank you for letting me know. Lishan is just joining. Lishan, we just started to discuss the homework solutions. We finished number 5, the first in the set of equations I sent. We finished number 5. We are on number 6. Okay, so 6 part 1 is X equals 2/3 or X equals 1. Part 2, X equals minus 2/3 or X equals minus 1. So in all the equations in that 6th question, you have a coefficient in the x square term. So if you were doing this by factorizing, the process is a little long. You can't immediately write the factors. Part 3, X is equal to minus 1/3 or X is equal to 2. Part 4, x is equal to minus 4/5 or x is equal to 4/5. Last one in that, fifth one, in number 6, x is equal to 2/3 or x is equal to 2/3. Repeated solution, so just one solution. X is equal to 2/3. Now I want you to be thinking about how the parabola, okay, Prasandi, thank you for letting me know. That's fine. We are discussing the homework, Prasandi. We are on the second question. I mean, it's the 6th question. We discussed, we marked number 5, we are marking number 6. Yeah, that's okay. So Afra is asking whether it is okay to write for the 4th one, you have the same number, positive and negative of the same number. So you can combine them and say plus or minus 4/5. That's fine. I think that's what you're asking, right? Is that what you're asking?
Yes, Miss. Thank you.
Yeah, okay. Right? Something that I want you to be thinking when you solve quadratic equations is visualize a parabola. How does the corresponding function, the word function should come to your mind. If this was the function y equals da da da, how would that parabola look like? So for this last one, it's the parabola, you check the sign of the x square term, it's positive, so it's a smiling parabola, and it's just touching the x-axis at 2/3. Right? When you have two distinct solutions, your parabola is crossing through the x-axis at these two distinct points. So always make that connection in your head so that it gets brushed up a lot, so that it sinks in properly. Because that's what's new that you learned in this quadratics chapter in advanced level, because you have learned how to solve a quadratic equation in O level. Why are we doing the same thing again? We are doing it with a little bit more understanding, a deeper understanding about what's going on. So you have to let all that sink in when you do these questions, not just do them mechanically, but then really think about how this relates to the function, right? Then number 7. Last question in that. So the equations you had in number 7 were not given in that format, ax squared plus bx plus c equals 0, in the ready format. You had to rearrange the terms into that format. That was the only difference between 5 and 6 and 7. Okay, so hope you got that, you found that okay. So 7 part 1, x equals minus 4. Hi Netmi. All right, okay. So a couple of you have had connection problems, right? So you're joining a little late. So just for everyone's information, again, let me say, we are going over the solutions of your homework. The first picture had 3 questions, number 5, number 6, and 7. So we are on number 7. I will quickly show you everything before we wrap this up for those of you who missed it to mark your answers. So number 7, part 1, x equals minus 4 or x equals 5. Part 2, x equals minus 3 or x equals 4/3. 4/3, which you may have written as 1/3. It's an improper fraction, but you can leave it like that in these cases. Now, please, you have to stop me and tell me if you have not gotten any of these solutions. Okay, you have to let me know if you have not gotten these answers. I trust you on that you would tell me if you have not gotten these answers. Okay, so your silence tells me that all of you have gotten these answers, right? Part 3, number 7, part 3. X equals 2, just one answer because it's repeated. It's the same answer again. So this parabola is just touching the x-axis. Is it a smiling one? Yes, it is a smiling one, and it's touching the x-axis. Part 4. Now, if you look at the equation in part 4, let me just quickly take you to part 4 question, because I want to bring your notice to something. So this part 4, this is the question, right? Part 4, 2x plus 1 equals 15 over x. At a glance, you might not identify it as a quadratic equation because it doesn't have an x square term. You know that a quadratic equation is an equation where you have largest power of x is a square, x square. But this doesn't have a square. You wouldn't realize it until you get rid of that fractional term 15 over x by multiplying by x throughout the equation. Until you do that, you might not realize that this is a quadratic equation. So I want you to pay attention to that too. Even this last question, 3x plus 8 over x equals 14, it might look like a simple linear equation, but it is not. Because x is in the denominator, then when you get rid of those fractional terms, you end up with a quadratic equation, right? Okay, even the fifth one. So the last three, they don't look like quadratic equations, right? Okay, so fourth one answers are x equals minus 3 or x equals 5 halves, or that is 2.5. Part 5, x equals minus 2 or x equals 3. And the last one, x equals 4 or x equals 2/3. X equals 4 or x equals 2/3. Okay. Then we go to the next set of, let me first find it. I have to, give me a moment, I have to open it. The next was a set of inequalities. That was also from your textbook, a different exercise. This is what I gave you. This is exercise 2F, question number 3. This question that I gave you was from exercise 2F. If you need to note it down, once you get to your books, you can find it. So you have a bunch of quadratic inequalities. So the way to solve these, we learned how to solve this. It's just one method. And that method heavily relies on a graphical approach. The first step, you do a little algebraic manipulation just to find factors. You factorize this to see, visually to see where the parabola cuts the x-axis. And then once you have that information, you go and sketch your parabola. And by just looking at the parabola, you can answer this inequality. You can solve the inequality, because it's asking where the parabola is positive or where it is negative, where it is above the x-axis or where it is below the x-axis, and so on. Because when you always arrange all your terms onto one side, you always have 0 on the other side. So it's going to be less than 0 or greater than 0. So it's going to be, is it positive, is it negative, something like that. So that trick that we do enables us to solve any quadratic inequality using that single method by sketching. So let's check that. So number 3, solutions are, number 3, part 1. P is between 1 and 4, excluding 1 and 4. What do I mean by excluding? 1 and 4 are not included. You don't have the equal sign for 1 and 4. P cannot be equal to 1 and 4, but between 1 and 4. Greater than 1, less than 4. Okay. This is an inequality. This is a single range. That's why you can put it together as a double inequality. This too we discussed last time. This is a single range from 1 to 4 on the number line, on your x-axis number line. Part 2 are two separate ranges. So you have to give them as two separate inequalities. P is less than or equal to 1, or you combine the two inequalities with the word or. Your P can't be in the two ranges at the same time. You can't say and there. It's or. So P is less than or equal to 1, or P is greater than or equal to 4. P can be any number less than or equal to 1, or it can be any number greater than or equal to 4. Part 3 again is a single region. Single region. X is between -2 and -1, including them. Including them. It can be equal to -2 and -1 too. If you illustrate it on the x-axis line, the two circles shaded and in between. Part 4, again two separate regions. X is less than -2 or X is greater than -1. Now this is really good. So no one got anything wrong yet? That is great. I hope that's the case, okay? The reason why you are not saying anything is because you got everything correct. I will assume that. Okay, part 5, again, two separate regions. Y is less than -1. Okay, somebody's messaging. Aha, okay, Afra. So my assumption, I think, is right. You all have gotten everything correct, right? That's why you are not stopping me and asking me, how do you get that answer, right? The reason why you don't have such a question is because you have all the answers I'm giving you, right? So part 5 is Y is less than -1 or Y is greater than 3. Okay, Afra. Part 6, single range. X is between -4 and 5, including -4 and 5. Okay. Did you get this for the 7th one? 7th one? Okay, yeah, right? That looks weird. Is that even a solution? What are you saying? Q is not equal to 2? Do we get such an answer for an inequality? How many of you got this or didn't get this? How many of you got this? Yes, Afra, I will. Let me first see. Part 7. Okay, let us go to this. Part 7. Q squared minus 4Q plus 4 is greater than 0. That one, right? Okay. So this is part 7. Oops. Sorry, why am I not seeing this? Okay. This is part 7. Q squared. I will write a little slow because I know there is a lagging. So in order for my voice to sync with what I write, I need to write slowly. Q squared minus 4Q plus 4 is greater than 0. Okay. Nice. So it's already in the arranged nice form. I just have to factorize this. So does it factorize nicely? Yeah. It's going to be, if I write it like that. So you're thinking of 2 factors of plus 4 that would add up to minus 4. That is minus 2 and minus 2. So you have Q minus 2, Q minus 2. Repeated in terms of solutions, repeated solutions, right? In terms of roots in the graph, it's just 1. It's cutting at, or that means it's touching at 2. So your parabola, I'm going to sketch it now, is like that. and your x-axis is not crossing through it, it's just like that, and that it's touching only at one point, which is 2. Right, okay, so that so far so good. Now what do I have to think? What are they asking me? For what value of q, oh, this is not x, this is q, q-axis, right, q-axis. What for, so this is to solve, right? That means for what values of q is this expression greater than 0? Let me repeat that. For what values of q is this expression greater than 0? Now I have graphed how that expression behaves for different values of q. That is the function, that's the meaning of function. I'm showing how it is functioning, how this expression is functioning for different values of q. When q equals 2, the value of your expression is 0. That's the only point where it is 0. I want to see where it is greater than 0, where it is above the q-axis. It's above the q-axis for all these q values. What are those q values? Everything except 2. Q, for any value that q can take other than 2, you put in any value other than 2 into this, you always will get a positive answer. That's what this parabola is showing me. My value of the expression is greater. Now you have to, right, somewhere you have your y-axis. Y-axis means, what does this y represent? The value of this. This is what y is. Right? And it's positive, it's positive, it's positive throughout here, and it's positive throughout all those places. So one way of saying that is, how do you say that? I can say when q is smaller than 2, or when q is greater than 2. Is that right? Because it's only at 2. It is not greater than 0, it is 0. Okay. Right? So you can write it like that too. You can give your answer like that. But what does that, like, you can just say q is, that means q is not equal to 2 means it can be anything other than 2. When you say it cannot be equal to 2, that means it can be equal to anything else. So this is a smart way of saying the same thing. But if you have written like that, that is correct too. Is this clear? Now I need a quick yes or no. Yes, okay. From everyone in the chat, yes, 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 no, 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 whatever that you want to say. Clear? No questions? Good. Very good. Please be like that, okay? Quickly respond. See how interactive then it is? Good, great, okay? Then I also feel like you're actually there. Right, okay. Then, going back, that was part 7. Part 8. Part 8, solution is that y is less than -2 or y is greater than 4. Hope you have that. It's that, yeah, that's part 8, no? Part 8. It's already in factorized form. You have nothing to do in that. You just straight away plot, like sketch the parabola, isn't it? That part 8 inequality, the, no, I'm sorry. If that is an 8, you can't. So you have to first remove that bracket and move the 8 to this side. make a 0 on the other side and factorize again. Sorry, I thought it's already factorized. It is already factorized, but you have an 8 on the other side. You can do it like that too. Like, can I ask you something? So you would only be able to answer what I'm going to ask now. If you have 100% understood this, how we use this graphical sketch of the parabola to answer our inequality. If you have 100% understood that, you can answer what I'm just about to ask you. Can I ask you that? I want to see whether, you know, it's a little challenging question, but let me ask you, let me go back to this. Now, that 8, what you have in part 8, it is 8, right? Yeah, part 8 is y, that's y, okay? It looks like a gamma. Y times y minus 2 is greater than 8. Okay. Now, did everyone remove this bracket? And then did you bring the 8 to this side? And is that how you did it? Like, okay, so let me divide the paper onto 2 parts. So this is one way in which you can do it. So since it's not a 0 there, you have to first make sure. So I will remove this bracket. It's y squared minus 2y, and then I will bring the 8. That's what I will have, right? And then factorize. Does it factorize properly? Minus 8 y minus 4y plus 2, right? Then you do your parabola. Here's the x-axis. Sorry, it's the y-axis. I mean, don't think now, oh wow, the y-axis came to the horizontal. Did it suddenly become the horizontal? That's not what has happened. They have just used the letter y to represent this unknown. Okay, so this can be very tricky. You don't get confused. So these values are called y now. Okay, it doesn't mean the y-axis has come here. It's just because they are calling. They have chosen to call this unknown y, okay? And this is minus 2, this is 4. And then you would be thinking, where is my parabola greater than 0? Okay, here and here. So that means 4 onwards, that way, and before minus 2. And then you would say, when y is less than minus 2, or when y is greater than 4, right? Okay. Can you think of a different way of doing this? Keeping the inequality as it is, because here, this already represents a parabola without the 8. This is a different parabola, just this. But here I want to see where the parabola is greater than, not 0, where it is greater than 8. Now let me sketch this parabola. Let me write it first. So y minus 2 greater than 8. Let me keep it like that. I'm going to sketch this parabola. Where does that parabola cut the, what are the 2 points where it cuts the x-axis? At 0 and at 2. At 0 and at 2. Now notice it's not the same parabola. This is different, right? This is this. This is this. This is just y squared minus 2x. Sorry, 2y. Okay? I don't know whether this will confuse you, but this will enlighten you if you have really understood what we have done so far. I mean, it's some additional insight for you. Now, I want to see where this parabola is Greater than 8. Where's 8? So let us have the horizontal axis. Let me call it, vertical axis. Vertical axis. So there will be 8 somewhere here. I want to see where the parabola is greater than 8. So wherever that 8 line, if you think of the 8 line, higher than that line, not 0, right? When it is 0, you just check, you just take the x-axis, because that is 0 line. Y is 0 on the x-axis. But now we have 8, so you think of y equals 8 line, and where your parabola is above that line. Do you see that? But to answer that, you have to know these 2 points. So then it will be above, so from here onwards, whatever that value is, and then above that point. My diagram is not very clear. So this point onwards and before this point. And if you will see, if you know how to find this, this would be -2 and this would be 4. Those 2 points where this horizontal line crosses the parabola. Okay, so that's just some extra thing. If any of that went into your heads, good. If nothing went into your heads, that's good too. It doesn't matter, okay? Because you're not supposed to like, but if you understood that, that would be great. We will be thinking, you will be learning about that in the next topic actually, which is coordinate geometry. So it's not that far away. Right. Then let's quickly finish this off. Number 9, x is between -2 and 1/3. Number 10, 2 separate regions. Y is less than or equal to -12, or y is greater than or equal to 6. Don't forget the equal sign. Make sure you have put the equal sign there. Y is less than or equal to -12, or y is greater than or equal to 6. Number 11, one region, x is between 1 and 3, including 1 and 3. And the last one, y is, okay, the point where y-axis 8 cuts the graph is the solutions for the inequality. Afra, you're talking about what I just did, the earlier one, right?
Yes, miss.
Yeah, so the point where the y-axis 8 cuts means the point where the y equals 8 line, you know, y equals 8 is a horizontal line, where that line cuts the parabola. That's where you have to look at to answer that inequality as it is. You have to see where your parabola is above the line y equals 8.
That's what I meant, miss.
Yes, that's right then. Yes. Okay.
Yes, miss. Thank you.
Welcome, Afra. So that last one is y is less than -12, or y is greater than 3/5. Okay. Right. So do you all feel confident and comfortable in solving quadratic equations and quadratic inequalities? Are you all okay, completely okay with that?
Yes, miss.
Yes, okay. So let me quickly take you to, we are going to finish this topic today. Let me just show you line of topics. In quadratics, if you remember in the beginning of our note, we put everything into this nice, like a, because it's everything about quadratics, quadratic this, quadratic that, quadratic this, right? So we have come to the last 2 topics. So we will today be looking at how to solve a pair of simultaneous equations when one equation is a quadratic equation. And we will also look at some equations that might not look like a quadratic equation at once, but to see they are quadratic equations, I call them, this is not a standard term, this is my, I made this up. I call these equations as equations, quadratic equations in disguise. You don't know that they are quadratic equations until you just, you know, remove their mask. They are quadratic equations. So there are certain equations that do not look like quadratic equations, but they are quadratic equations. So I mean, they can be turned into a quadratic equation and be solved like a quadratic equation. So they are called quadratic equations in disguise. So this is what we are doing today. So put your next topic. I think it is 1 point. If I quickly take you, so solving quadratic inequalities was 1 point. Let me just check that. It was 1 point. Oops, it was 1.4. So this is 1.5. Okay, let me write the topic for you. Let me take you to the writing pad in a moment. Give me a moment till I fix this. I am going to call this quadratic 1.5. I will show you. I will take you to the writing pad. Give me one more second. Right. I call this these equations are called. You know what a pair of simultaneous equations are. When we, in our revision, pre-algebra revision, you did some solving simultaneous equations questions. So typically, a pair of simultaneous equations are two equations, two equations with two unknowns, and each equation is a linear equation. What do I mean by that? Both your unknowns, you can have xy, ab, mn, pq, doesn't matter what letters are used. They don't have powers, just m, n, p, q. You don't have p square, p cube, different powers of those unknowns. The power that means was 1. So they are linear. Okay, they are called linear equations. Both your unknowns had a power of just 1. Now, what you are going to see here are non-linear. We call them non-linear simultaneous equations. That means that can be, you know, really a broad topic. You are only looking at a very simple case where in your pair of simultaneous equations, one equation is a typical one that you normally see. The other one could have a square term of one of the unknowns or both of the unknowns, right? So these are called non-linear simultaneous equations. Or I would, to relate it to quadratics, I will put the topic as simultaneous equations with quadratics. Okay, so let's write the topic 1.5. So you write with me, simultaneous equations with quadratics. In brackets, I will give you the topic that the textbook has, nonlinear simultaneous equations. Non-linear. Okay. So before we jump into nonlinear simultaneous equations, let me quickly take you back to, you already know this, your O-level, what you have learned in your O-levels, how to solve a pair of linear simultaneous equations. You learned 2 different methods for this. So we are going to quickly recall those 2 methods because we are going to be using to solve nonlinear simultaneous equations. Also, we are going to use one of those same methods. It's nothing new. It's just, I mean, yeah, you could have done this by yourselves, okay? What are the 2 methods you have learned to solve linear simultaneous equations? Who can remember these words, the fancy mathematical We say this method and that method. What are the two methods? Does anyone remember? To solve a pair of simultaneous equations, you learned
Miss, what was the question?
what are the two methods you learned to solve a pair of simultaneous equations in? That right, Pesandi? Yes, Pesandi tells me the name of one. One method is called substitution method. And the other one, there are two methods. To solve a pair of simultaneous equations, you have learned two methods. One is substitution method. The other one is make the two equations equal. What does that mean? How do you make two equations equal? Then would you have three equal signs in one line? Because you take one equation, it has an equal sign already. You just take that and equal to the other equation. You'll get something with three equal signs. What do you mean by make the two equations equal? See, when you say I think I know what you mean, but see the way you say it, you're completely using wrong language. Can you try again saying, but there is a nice word for it. One is substitution method. No one can remember. That's bad. This is your O-level. Anyone? Okay. Because I don't want to waste time. Umasha is asking whether it is evaluating method. It's not evaluating, but it's close to that word. So Afra says, for example, 6y plus 9y. You would write that if your two equations were what? Yes, Akitmi. Elimination method. Does that ring a bell? Elimination method, substitution method, and elimination method. Okay, we are going to quickly recall. Yes, Lishan. Of course, it's having the same terms. No, what is that? We don't do anything like that. What do you mean? What's that? On both equations having the same terms. So you take the same term in both equations and add them. Why do you do that? How does that make sense? No, eliminate them. Okay. Yeah, eliminate them. To eliminate you having the same. Okay. The thing is, it's not clear to me what you're saying. If what you're saying is this, you add the two equations, not equal them. You add the two equations. Two equations can be added, right side to right side, left side to left side. You get a new equation. You add the two left sides and the two right sides. That you can do. You can add two equations. Can you equal two equations? What does that even mean, right? Yeah, that's what I said. So you can add them in the hope of certain terms get cancelled. Yeah, so you strategically add them sometimes, or sometimes you subtract. Right, so let's quickly recall. Now, it's very clear. I can see that you can't remember certain things here. So quickly, this is just recalling, right? Recall. Let's quickly recall solving linear simultaneous equations. This is what you have learned in O-levels. Solving linear simultaneous equations. And you write, there are two algebraic methods. These are called algebraic methods. What that means is, you are just manipulating your equations algebraically. You multiply by something, you add the two equations, you subtract them, you're just manipulating the equations algebraically. In contrast to this method, algebraic methods, there can be geometric methods or graphical methods of solving equations. You will learn that in the next topic, which is coordinate geometry. So that's why I say there are two algebraic methods, because there can be graphical methods too. Okay, algebraic, there are only two. There are two algebraic methods of solving a pair of simultaneous equations. Let me just write SEs, simultaneous equations. One, elimination method. Two, substitution method. And let's quickly take an example. Let's take a pair of simultaneous equations and solve the same pair using the two methods. Okay.
Miss, you're muted.
Was I gone for some time? What happened?
Miss, you just froze. That's it. Nothing.
Nothing. Like, was I gone for some time, or it was just like just a second?
I think you were gone, Miss, for some time.
Did you see me writing all this?
No, Miss.
Oh, really? This is the thing. I don't realize it. My screen looked fine. I was talking and I was writing this. Where did you lose me? In what line?
Solving linear simultaneous equations.
Ah, this one. Okay. Sorry about that. I don't know what happened. And the strange thing is, on my screen, nothing looked weird. It looked as everything was fine.
Yes, but I did tell you that you were stuck.
I didn't hear. So I didn't hear anything. Okay, so can you copy? I have written, there are two algebra. Oh my God, I was explaining what algebraic means here. You didn't hear that, no? There are two algebraic methods of solving a pair of simultaneous equations. This SE is for simultaneous equations. Algebraic means you take the two equations and you manipulate the equations algebraically. You multiply equations by a number, you divide your equations by a number, you add your equations, you subtract your equations. So you do stuff to your equations, you manipulate them in order to finally find what your two unknowns are. That's an algebraic method. On the other hand, there are graphical methods of solving equations. Okay, so since there are other methods, that's why I included the word algebraic. There are two algebraic methods because there are other methods of solving this. So they are simultaneous and elimination method and substitution method. And I'm going to take one example of a pair of simultaneous equations and solve them by using both methods. So I will do it side by side, parallel, just for comparison. You know this already. And you can get a sense of which method do you prefer? Can you answer that question? You can't. I mean, it depends on the kind of pair given to you. It depends. For certain pairs of simultaneous equations, elimination method would fit better than substitution. One might be better than the other one. It depends on the given two equations. So, example. Let us do one example. If I say solve, here are the two equations. 6a plus B equals 40. 4A plus 3B equals 36. Let's quickly solve them using the two methods. I will divide my page. I will do elimination method here. And substitution method here. This is all recall. This is all underline there. This is just recall, okay? This is just recall, nothing new. You're not learning anything new. You're just refreshing your memory. Okay, here itself, let me label my equations 1 and 2. In elimination method, what you would be trying to do is you would, now each of these equations have two unknowns. So if you look at one thing, like if you look at the first equation, can you just use that first equation to solve for A or B? You can't. Can you use only the second equation to solve for A or B? You can't. So what you have to, now we are looking for a value for A and for a value for B that would fit both of these equations. So in elimination method, what you would be trying to do is you would try to eliminate one of the variables and get a single equation with a single unknown. So you're thinking of a way to combine these two. What can I do to get rid of one of the variables? So if you look at it, first one has 6A plus B, second one has 4A plus 3B. If you can make a certain term the same, like either the A term or the B term the same, then maybe you can subtract the equations and get rid of it. So what's the easiest to do? The B terms can be made the same if I multiply the first equation by 3. So I do that. First equation multiply by 3. I get 18A plus 3B equals 120. Sorry about that, 120. Now let me write the second equation underneath this. This is just the same second equation. Let me call this 3. And this is still my 2. Now what can I do? I can simply, so these are the same term now. I have the same term in both equations. If I subtract the equations, now you have to know, what do you mean by subtract equations? Can you even do that? Now I hope you asked these questions when you were learning this originally in your whatever grade 9 or 10 or whatever. Because you know how to I can subtract numbers. 5 subtract 2. That is okay. In an equation you have these sides. You have two sides. And how do you subtract an equation from another equation? Like, did you really think about what that means and how that is possible? What that means when we say subtract? So you can subtract equations. What you do is left from whatever equation, you subtract whatever other equation. Then the left sides get subtracted separately and right sides. The two sides you subtract separately. That's what you do, right? So I'm going to do 3 minus 2. So that means this minus this and equals that minus that. Okay, so you already know this. I'm just taking you through it slowly. So if you write this like in a line, it would be this bracket minus this bracket. So what the 3b will cancel and you will get 18a minus 4a is what? 14a. 120 minus 36 is what? 120 minus 36 is 84. Divide both sides by 14. You get A is equal to 6. That's one answer. Then you can put it back in one of your equations, one of your original equations, 1 or 2, whichever you like. I will do substitute, sub in, I'll take the first one. So 6 times 6 plus B equals 40. B is equal to 40 minus 36. That gives me B equals 4. Is that clear to everyone? I mean, this must be like cheese, like piece of cake to you, right? Okay, substitution method. What do you do in that? Your final aim is somehow to obtain a single equation with only one unknown. That's your aim, because that you know how to solve those equations. Any equation with one unknown, you know how to solve. So you're thinking of a way to combine these two equations to get a single equation of one unknown. In substitution method, you for example, now in this first equation, you can find what B is in terms of A, and then substitute that for B in the second equation, right? So what you would be doing here is, I take the first equation, make B the subject in that. Make B the subject. Now go and put that in the second equation. You substitute. Let me call this. Substitute 3 in 2. I get 4A plus 3. For B, I put this whole thing. See what I have got? I have a single equation with just one unknown, and I know how to deal with that. So let's go ahead and solve it. I will take the A terms to the other side. You see, you get the same numbers. And then you put it back again. The rest is the same. Sub that in, whatever you want. And you get, so I'm not showing you that, you get that. Right? This was just recall. Now let's look at, I'm going to now give you a pair of non-linear simultaneous equations. That means one of the equations will have a quadratic. It can even have any other thing. You are just studying here. What if one of the equations is a quadratic? Because we are in the quadratics topic. Okay. So let's take a non-linear simultaneous equations. I don't think we can finish this today. Maybe we can. Okay. Then put a subtopic, solving. This is what you are learning new now, solving non-linear. Very easy. There's nothing big here. Very easy. The same thing you do. Non-linear. Let me say SE, simultaneous equations. And let's start with a example, but let's write what a nonlinear means. Okay, so write with me. Nonlinear simultaneous equations are nonlinear SEs are when at least one equation is not linear. That means, now you know what linear means. I have told you. Linear means the power of your unknown is 1. Non-linear means power of your unknown is not 1. Something else like 2 or 3 or whatever, right? We will see how to solve a nonlinear, a pair of nonlinear simultaneous equations when one equation involves a quadratic. That means a square of one of your unknowns. Okay? Let's jump into an example. I mean, the method we are going to use here, you will see. I will ask you which method might be more suitable. Here's my first example. Solve. So one of your out of your pair of simultaneous equations, one will be a normal one. And I'm giving you in this form. Y equals x plus 5. That's one equation. Do you immediately see a difference in the way I gave it? Usually in your simultaneous equations, they are arranged so that your unknowns are on one side and your number is on the other side, right? But here, this is how I give you. It is easy when I give it like this. It's like a function, y equals x plus 5. It's like the equation of a straight line graph. And here's the second equation, y is equal to, they're both given as y equals to. So your two unknowns are x and y. It could be m, n, p, q, a, b, anything. The letters I have used are x and y. And in one equation, both of x and y have power 1. In the other equation, you have x squared. So this is a quadratic, right? Do you immediately see what you can do here? So it's going to be either the elimination method or the substitution method. What do you very easily see here? I have y is equal to this and y is equal to that. What can I do? Substitution. I mean, put this y in here, right? You substitute. You have y being made the subject in both equations. Or you can just think of as you equate the two right-hand sides because they both are equal to y. Okay, do you see that? So let me write use substitution method. Substitution method. Simply you can say 1 is equal to 2 because I have the same letter equated to two things. I can just equate them. Here you are not equating the equations, you are equating the right hand side of the two equations. So x plus 5 is equal to x squared plus 7 because they are both equal to the same y. Now you know how. Now you have a single equation and one unknown, and it's a quadratic equation. You solve it. You solve it. Go ahead and solve it. I will also slowly solve it. I want you to solve it before me. Oh, I'm sorry. Wait. This is minus. I'm sorry. This is minus. Okay. No, still it's wrong. I think it's not minus. I have made a mistake here. Because I want to give you something that gives you good round answers. Okay, here's a problem for you. I want this to be -2, just so that we get a nice quadratic to solve. We don't need to make that complicated here. You know how to solve quadratics. If I want this to be -2, how should I change the numbers? You tell me. How should I change that? I should keep this as +7 and change that to, I think, minus. No, I'm messing this up. Let me. Can you think? This is what I want to get. What number should I keep? Reverse engineer. You're reverse engineering the problem. I want this. I want to get this. What sign? What should I have?
Y equals x minus 5, y equals x square minus 7.
X minus 5 and x squared minus 7. Okay, this will have nice solutions. That's why. So since your x term was a square term, you get 2 answers for x. Oh, I'm just seeing your it just popped up the chat box. I'm just seeing your messages. Yeah, -7 and -5. That's right. Okay, send it to. Okay. So you get 2 answers for x. Then you would get 2 corresponding answers for y. When x equals 2, so you can again go back and substitute these 2 solutions in either one of your original equations, either in 1 or in 2. It's easier to take the linear one, isn't it? So let's substitute in sub in 1. If you sub x equals 2 in the first equation, for y you get 2 minus 2 minus 5, that is -3. When x is equal to -1, y is equal to -1 minus 5, that is -6. Okay, so you get 2 pairs of answers. X equals 2 and y equals -3. That's one pair. Or x equals -1 and y equals -6. 2 pairs of answers. These 2 values would fit into the original equations. So do these two answers. Okay. I can quickly show you something. This you will be learning in the next chapter, coordinate geometry. But since you already have some visualizing ability, let me quickly show you what this graphically means. Now you can already see these two equations. Don't they look like the equation of some graph? This is the equation of a what? Your first equation is the equation of a
Straight line graph.
straight line. Your second equation is the equation of a
Curved graph.
what kind of a curve?
Parabola.
Parabola. This is a straight line. This represents graphically, if I plot y versus x and plot all possible, it's a function. It's a straight line function. And this is a parabola, it's a quadratic function. Graphically, what you got here, the two pairs of answers are this. Now, if you think this is useful, you just copy this too. You will be learning about this in the next chapter. Your first equation is a straight line, like this. So this is the graphical meaning of what you just did. This is y equals x minus 5. I'm just drawing the line without the grid. And then you have your second equation was a parabola, x squared minus 7, that's positive x squared is positive, so it's a parabola like this. That's it's terrible looking parabola. I'm sorry about my. This is y equals x squared minus 7. Guess what you got for your answers. Guess what you got for your answers.
The coordinates of the point where the parabola and the straight line intersects.
Yes, you got the coordinates, xy coordinates of the intersecting points of the parabola and the straight line. Why? Because it's only at those 2 points. It's only here and here. The value for x and y both satisfy. These are the only 2 points that lie both on the parabola and the straight line. So these values, this has to be minus 1 comma minus 6. This is 2 comma minus 3. So those are the only xy values that fit both the line and the parabola, because those are the only 2 points that are on both of them. Does that make sense? So this is a beautiful thing. In the history of mathematics, it took a long time for people to realize this relationship between something that you do algebraically here and the connection that has with a graph. It's like 2 different worlds were connected. In coordinate geometry, which is your next topic, this is what you are learning, where algebra and geometry come together. Okay, so if you think this diagram is helpful, just sketch it and keep. It'll make a better and better sense as we go along the topics. Okay. Then shall we? I will. So there's nothing much. Okay, you just need to practice that. Then can I ask you something? Do you think there could be cases where if I give you a straight line and a parabola, like a pair of simultaneous equations? Oh, does Aisha have a question? I just joined since I had. Oh, really? Weren't you like you got? Oh, right. Okay. Okay, Aisha. So I'll send you the recording. Okay, to catch up what you missed. So if I give you a similar pair of simultaneous equations where one equation represents a straight line and the other equation represents a parabola, could there be cases where you would not get any solutions? Would you always get 2 pairs of solutions?
No, unless the straight line really intersects with the parabola.
Right, yeah, right. If now a pair of nonlinear simultaneous equations that you are learning to solve here, always one of the equations represents a line. The other equation always represents a parabola, because one of your equations is a linear equation and your other equation is a quadratic equation. So they graphically always, one represents a line and one represents a parabola. And if you think of how these parabolas and lines could be in space, in a plane, you can have your parabola and the line not cutting at all. What if I give you the two equations such that your line does not cut the parabola? That means the two simultaneous equations would not have a solution. What else can happen? Any other case? So you can have two pairs of solutions, like the one we did now. You could have a pair of simultaneous equations. When you try to solve, no, you don't get any solutions. Anything else that can happen? Only one solution, Senithu. Yes. Can you describe to me how that graphically looks like? What must happen for you to have only one solution? One pair, one x and one y.
Tangent?
Yeah, your line is a tangent. It's just touching your parabola. Not crossing it at 2 points, but just touching it at 1 point. It's a tangent to the parabola. Yes. Okay. Isn't that cool to know that? Like, see the connection between solving a pair of simultaneous equations, how that connects to a graphical picture, and that how that, you know, doesn't that deepen your understanding of solving simultaneous equations, right? Okay, so there is a lot of, let me switch off this. I don't think I need that. Okay, now I'm letting you explore all this. Look at this, how we solve this equation, pair of simultaneous equations. Let me put this so that you can see everything on the screen now. Now, I want you to tell me, look at this method. Now we solved it algebraically here using the substitution method. If I walk you through the steps again, since it is substitution method, what we did was we substituted y in one equation to the y in the other equation. In other words, we simply equated one of the sides. So here in this case, right hand side of the two equations, because they both are equal to the same y. So you equated them and you solved it. Now, just now, you told me that you could have 3 different cases when you solve a pair of nonlinear simultaneous equations like this. The 3 cases are, you could get two pairs of solutions, like what happened here, or you can not get any solutions, or you can get just one pair of solutions, one x and one y. One pair, nothing, 2 pairs of solutions. These are the 3. Can you look at the process here that we went through, and tell me, is there anything in this process? Is there anything that we can do in this process that would tell us how many solutions we are going to get in this pair of equations without coming to the end? Now, before you come to the end of this, is there some step somewhere where you are able to determine whether this is going to lead me to 2 separate pairs of solutions, or 1 pair of solution, or no solutions?
The moment you come to a quadratic equation?
The moment you come to the quadratic equation, the moment when you combine, see, you combine the 2 here, and you get a single quadratic right here, this one. At that step, you can check something to see whether this is going to lead me to 2 1 or 0 pairs of solutions, what do you have to do? You check the determinant. Not determinant, discriminant. There is something called determinant too. I always mix up those two words. The discriminant of this would tell you whether you are going to have, because if you get 2 solutions for x only, you would have 2 solutions for y, right? So right at this step, by deciding whether this is going to have 1 solution, 2 solutions, or none, you can say whether the pair of simultaneous equations are going to have a pair of 2 solutions, a pair of 1 solution, or a pair of no solutions. Is that clear? This is some deep mathematics, and like for your level, because you haven't even sat for your, some of you have not even sat for your O-levels yet. This is something nice to think. We will be touching on this again in coordinate geometry too, but I'm going to give you that as a note, a little note here, okay? Shall we write a little note? I don't think we can finish this today. I thought we could. Right, shall we quickly write a little note? I'm going to read, you write under this solution.
Miss?
Yes, Afra?
Miss, is it possible to solve nonlinear simultaneous equations using an elimination method?
That is a good question. Now, if you look at this example I've given you, this pair, okay? In elimination method, what do you try to do? You try to eliminate. So if I take you back to the, do I have it here? In the elimination method here, okay? You try to add or subtract your equations to eliminate one of your unknowns. You try to add or subtract your equations, the 2 sides of your equations, to eliminate one of your unknowns. Can you do that here?
Excuse me, Miss. Miss, you can make X the subject in the...
Make X a subject? Okay, let me read. You have already written.
Make X the subject.
Can you make X the subject? Yes. Okay. Okay, Aisha.
And substitute that in place of it.
Right, Aisha. Your question is clear. Aisha is asking whether can't you make X the subject in the first equation and substitute that in the second equation for X? Can do. But you will see that's harder. This is the, why do you want to make X the subject? You already have Y made into the subject. It's already given to you with Y as the subject. Why do you go and change it to a different subject? Isn't it? In the given pair, I need this. In the given pair, Y is made the subject. So it's like that step is done for you. Here you go. I have made Y the subject for you. And then you say, no, I want to make X the subject. It's like that. I mean, there's nothing wrong. You can do that. You can make X the subject and substitute it here, right? And then you would get a quadratic equation of Y. You will end up with the same answers. This is a nice, this would lead to a good exploration. You can explore this, but do all different kinds of things. And then what Afra, I think, asked was, can't we use elimination method? Yeah, do you see now both equations have the same Y term? Then if I subtract, I can eliminate Y. That would work too. You would still get the same equation. Okay? See, this is really good. I mean, you're trying, I have done it in the quickest, best way. Best in the sense it's faster. Other methods, they are all correct. All the methods that you suggested. What Aisha said, let's make X a subject and substitute, works. And Afra's suggestion, can't we do elimination? Works, can do. Okay. So have that freedom. I want you to have that freedom. You just go and do what you want, as long as you are not violating any mathematical, like, you know, the rules. You can do anything you want. You would end up with the same answers. Okay. Shall we quickly write a small note?
Okay.
Okay. So I will dictate. You write. This example shows. This example shows that when solving a pair of simultaneous equations, when solving a pair of simultaneous equations, when solving a pair of simultaneous equations where one is linear, sorry, where one is linear within brackets, line graph, close bracket, and one is a quadratic, where one is linear and one is quadratic, where one is linear within brackets, line graph, close bracket, and one is quadratic. And one is quadratic within brackets, parabolic graph or parabola graph, close bracket. The two equations boil down to, a single quadratic equation of one of the unknowns. A single quadratic equation of one of the unknowns. That's the one I have highlighted. You can do the same. You can highlight and keep in the example that you did here. The two equations boil down to a single quadratic equation of one of the unknowns. Whichever method that you just that we just discussed, that you use, you end up with a single quadratic of one of your unknowns, either of y or of x. New paragraph. Do you hear firecrackers? Something is going on. There are firecrackers being... Anyway, new paragraph.
Means there are firecrackers all over the place.
There are too? Is there anything happening today?
Miss the oath ceremony.
Ah, okay. Okay, I'm not in this world. So that's happening today, right? Okay, so, okay. Yay. Okay. New paragraph. Depending on the number of solutions, depending on the number of solutions to this single quadratic equation, depending on the number of solutions to this single quadratic equation. For quadratic equation, you can just write capital Q, capital E, abbreviate it to this QE. We can say how many pairs of solutions, how many pairs of solutions the original pair of simultaneous equations would have. The original pair of SE would have. Okay. The discriminant of Lishan says, even at his place, he can hear the firecrackers. And Pasandi too. So it just happened, right? We missed it, didn't we? We all missed it. They must be showing it on TV. The discriminant of the single, okay, Senithu is asking, Miss, in the example we discussed, if the x square term is replaced with x cube, will there be 3 solutions? Yes, at most. Good question, Senithu. So I think you're starting to see the pattern here. Quadratic, if the power is 2, we are getting 2 solutions for a single variable. For x you got here, for x you got 2. So correspondingly, y got 2. So there were pairs of 2 pairs of solutions. If you have x cube, that would correspond to 3 solutions. X to the power of 4 solutions, and so on. So the cube graph, good. These are all good questions. Does anyone know how a cubic graph looks like? The basic shape of a cubic graph. The basic shape of a quadratic is a parabola. Now you learned that. Does anyone know the shape of a cubic graph? Cubic
like a C and another C in the. I never described it.
C and another C. It's close, like something and another something. It's not a C though. It looks like this.
It's like 2 halves of a tree.
2 halves of a tree.
Like a wave.
Like a wave? Who said that? Okay, so this is off topic, but it's all math, right? So like the basic parabola, like this is your x and y. For the quadratic you get like this now. This is what? Y equals x squared. Okay? Y equals x cubed. You know what happens? This arm, if I call them like the 2 arms, okay, the 2 arms of the parabola, this arm gets flipped over and it continues. So this is how, if I trace over it, so this part would be the same. And then from here, it will go like that. This is y equals x cubed. And any cubic graph would have that basic shape, this shape. It's like a, so it's not a C, it's not a wave. If you, waves go like that, right? It's like a worm, like a snake. Yes, snake. It's like a snake. Okay, so if you think of a straight line and a graph like that, at most you can have 3 points cutting. Think of a line where if you place a line here, no solutions. If you place a line like that, you can have 1 solution. If you place a line like, I can't draw it, you can think of different placements of a line so that you will have different number of solutions. Solutions are where they cut, basically. We're actually discussing coordinate geometry here. Anyway, now the line that you were writing was the discriminant of this boiled down quadratic equation. Back to the note. The discriminant of this boiled down quadratic equation QE.
I'm sorry, is the discriminant of
this boiled down. I said the two pair of the simultaneous equations boiled down to a single QE. I'm talking about that. The one you be highlighted. I'm talking about this, right? The boiled down. I'm using the word boiled down. So the discriminant of this boiled down QE will tell us how many pairs of solutions we get. How many pairs of solutions we get. Senith is asking, if there can be 4 solutions in that if we place a correct line right? No, I don't think so. How do you get, can you draw and show me how to get 4 points of intersection? It's only 3. Maximum is 3. Okay, Senithu is asking, Senithu is saying that you can place a line so that it cuts at 4 places. No. You just draw a few and see, okay? Maximum is 3. It can't cut at 4 places. Okay, so did you write that sentence? The discriminant of this boiled down QE would tell us how many pairs of solutions we get. And then write, I will quickly say again, if b squared minus 4ac, this is the discriminant of that highlighted one, okay? If it is greater than 0, that means we get 2 pairs of solutions. That means your parabola and your line are cutting at 2 points. Your intersecting points are your solutions. You can complete this note. If b squared minus 4ac is equal to 0, you have only 1 pair of solutions. That is when, I mean, you can draw it any way you want. This time I will draw the line like that. That's when it is a tangent, only 1 point. If your b squared minus 4ac is less than 0, no solutions. And actually we mean no real solutions, okay? No real solutions. That means the parabola and wherever your straight line could be like that. No intersection between them graphically. So your pair of simultaneous equations will not have any solutions because there are no values that x and y can take to fit both of them. That can happen, right? Okay. Is this clear? What I'm going to do now is, we have about 15 minutes. I'm going to quickly do the last topic as well. That is not hard, and then I can give you some homework, okay? I will give you some simultaneous equations to solve and practice for homework. Let's quickly go to the last topic. 1 point. This is quadratic equations in disguise. They are wearing a mask. You can't see that they are quadratic equations. You have to go and remove their mask. So your last topic in quadratics, is it 1.6? I think so. (1.6) quadratic equations in disguise. Okay. Again, nothing much new here. Let me show you one such equation. These are just equations, not simultaneous, just equations. They don't look like they are they are quadratic at a glance. Example. So this is the topic. Example 1. I will just show you a few examples, and you know how to recognize them. Example 1. Here's the equation. Solve x to the power of 4 minus 13x squared plus 36 is equal to 0. Now you look at this guy, and you can see that the highest power of x in this equation is 4. So it is not a quadratic, isn't it? Very clearly, it's not a quadratic. There is a square term, but the highest power is 4. So it's not a quadratic. But I call this a quadratic equation in disguise. Why do I say that? I can turn this guy into a quadratic equation. What I have to do is, in all of these equations you will see, you just have to do a relabeling. You relabel something and then it becomes a quadratic. See what I'm going to do. Can anyone suggest? I'm going to relabel something. I'm going to call something else. And then it's a quadratic. Can anyone see what that is? Okay, since this is the first example, I'm going to let means I'm suggesting, let's call this as this. I'm going to call x square, let x square be called, take one name, u or p or q or t, or doesn't matter what you, tell me a good letter you like. Shall we take u? I'm going to relabel x square as u. It's a relabeling. That's all that I'm going to do, relabeling. So if I'm going to call x square as u, what would my equation turn into now? Then x to the power of 4 I can write as x to the power of 4 is x squared square, isn't it? Square of x squared. Let me show you. This is x squared. That's right. Do you see that? So that is u squared, yes. So this becomes u squared. And this becomes 13u plus 36 equals 0. Now what is that? It's a quadratic, not of x, of u. Okay? Then is that okay? Where did the x go? No, that is okay. We have to now. So we will solve for u. You would find answers for u. If you know the answers for u, you can then find the answers for x using your relabeling, using your substitution. This is like a little little, I don't want to call it substitution because you will mix that word up with the method we had in simultaneous equations. It's a relabeling. Can you quickly solve this now? This is very easy now. So now remember, we have turned this into a quadratic equation of a different letter, different unknown now. That's okay. We will finally get back to our x. Okay. So let's solve this. I think this nicely factorizes. I will give you the factors: -9 and -4, -9 and -4. So you get u equals 9 or u equals 4. Okay. Senitu is, yes, Senitu, that's another way of doing it. Because now, since I'm discussing how an equation can be turned into a quadratic, that's why I use the relabeling. I will come to your method as well, and let's see how that works too. Now everyone can see what Senitu has written. He's suggesting a very nice, a different method of solving this, which works fine. Okay, the method I'm using here is by turning the given equation into a quadratic, because I see this looks like a guy who is disguised in a different form, but it's actually behind his mask I can see a quadratic equation. So that's the method I'm using. Okay, but your method works too. Let us quickly finish this off. So I got u equals 9 and u equals 4. U is something that I took. There was no u in the original equation. What is u? Now you bring back your x. U is nothing but x squared. Now let me go back to what is u? It's x squared equals 9. X squared equals 4. Okay. Senitu, by the way, that method, even though at once it looks like something that you can do, you can't do that. I will come to that. Okay. So now x squared equals 9. Square root both sides. X is plus or minus 3. X squared equals 4. X is what? Square root both sides. Square root, square root, square root, square root. Plus or minus 2. So you have 4 answers for x. X equals 2, minus 2, 3, or minus 3. Okay. Now, Senitu, okay. It's not, what is 23? You mean 36? What is 23? Anyway, so Senitu was suggesting to take an x square out. You can take an x square out only from these two, and that won't give you anything. I thought that would work, but that doesn't work. No, that doesn't work. So I think it looks like this is the only method. There might be other methods. You keep thinking, but this is a quick way of. Yeah, if you take the 36 to the other side, then what? No. Okay, so let me quickly show that. Okay, so if you do this, that's not going to work. So let us try. Let's try, right? Let's try and see whether these other suggestions work. X to the power of 4 minus 13x squared equals, you take the 36 to the other side. First of all, it becomes minus 36. Even though, suppose it was a minus number here, and suppose it was minus 36 here, and you take it to the other side, and then it is plus 36. And then when you take the square root, this is what you would do, right? What's the square root of this? I don't know. You can't take square root of each one. This is the square root of this whole expression. What is that equal to? We don't know. So you get stuck after this. This side, of course, if this was plus 36, you can say that is 6. Plus or minus 6. But this, you can take an x square out of this. This, you can do this now. You might not understand this, but you can do this. But then what? You can take an x square out of the square root, then it becomes x when it comes out. Anyway, I mean, that's not going to work because, let's not think about that. That's not going to work because we don't know how to simplify this. There is a huge breeze coming in. Okay. Miss, if it was 36, we can take an x square out, and do complete square. If you take an x square out, let's try it. Let's try. Sanith is saying, so like I did here, right? How do you complete square? Now the whole target is to isolate x, right? If we can't do that, then our method fails. So if you do this, then if that was 36, on this side you get plus or minus 6. What are you suggesting to do here? If the 13 was positive, if this was, no, even if it is positive, I suppose this is positive, then how? I can do this. I will show you. Out of these two, I take a x square out. Right? And then this can be written as square root of x squared. I hope you remember that. When we did surds, we learned this, how you can break this into two. Then this is just x. And then that. Now what? Now what? Then we are stuck again. If the 13 was positive in the original equation, yeah, so I made it positive here. Still it doesn't work.
Miss, is it 6 or 16?
6. Where did the 1? 1. It's 6 here. So what do we do now? So we get stuck at this point. From this point, we don't know what to do onwards. You see that you have an x here, you have an x squared inside here. We want to isolate x. We want to have x in just one place. Yeah, okay, so that method doesn't work. Let's quickly look at another example. So this is an example for an equation, for a quadratic in disguise. This indeed was a quadratic, because I was able to turn it into a quadratic, right? Let's look at another one. Example 2. Example 2. Solve x squared minus 2 equals 8 over x squared. Okay. Now you would tell me that is a quadratic. Do you think this is a quadratic? Now it already looks like a quadratic, but it actually is not. But it can be turned back into a quadratic. Why am I saying it's not a quadratic? Even though yes.
Can you show example 1? Because I couldn't complete completely.
Yeah, sure. Where is it now? Yes, example 1. Let me know when you're done. So you get 4 answers here.
Done, Miss.
Okay. So in this, it does look like a square because you see the power 2, but there is an x square in the denominator. Okay, in a quadratic you can't have x square in a denominator. If you get rid of that, you will see this is not a quadratic. It doesn't look like a quadratic. How do I get rid of this? Anyway, you have to get rid of fractional terms to solve. So if I multiply throughout, if I multiply everything by both sides by x squared, I'm multiplying both sides of the equation by x squared. So that means this side by x squared and that side by x squared. Okay, then I get x to the power of 4 minus 2x squared equals 8. So this has power 4. So it's like the earlier example. So if I bring everything to one side, it's not a quadratic, but it's a, we call this a quartic. Power is 4, they are called quartic. It's a quartic equation. But just like we did earlier, you can turn it into a quadratic by doing a clever relabeling. Let's relabel. Let x to the power of 2 be called, shall we use t? Just for fun, change the letter. So this would become what? This is, now you have to see it, huh? This is x square square. So that is t square minus 2t minus 8 equals 0. That's a quadratic. That's a quadratic. Let me highlight it when I get the quadratic. Originally it was not a quadratic, but now it is a quadratic. So minus 4 plus 2, right? So you get t equals 4 or t equals minus 2. So I solved for t, but t is something that I used. What is t? T is x squared. Bring your x square back. This t is nothing but the x square. So I have x square equals 4 or x square equals minus 2. Let's square root. X is plus or minus 2. What happens here? No real solution. Can you square root minus 2? Nope. That doesn't give me any solutions. Oh, my pen is over, I think. So you have only two answers, 2 and minus 2. Okay, is that clear?
Clear, miss.
Clear, okay. I don't want to rush through. The third example is a little different. I don't want to rush through it, but now you got the idea, right? These are called, I call them quadratic equations in disguise, which means I can turn them into, they don't originally look like a quadratic, but I can turn them into a quadratic equation and then solve it like I'm solving a quadratic equation by making this nice relabeling. Always what works here is you do a relabeling. You call something by a different letter, then that makes your equation become a quadratic in a different letter. But you can finally get back to your original letter in the original equation. Okay, I'm going to stop from there. We have to do one more example in that. And with that, our topic is over. I want to quickly show you.
Miss, can you show the bottom part of the page?
Yes. There you go.